In the middle of the night, on the 3rd of September 1859, the sky was suddenly lit up as bright as day, with aurora that was seen as far south as Cuba. Telegraph operators were electrocuted, wires sparked, and fires were set. Eerily, telegraph messages continued to send themselves even after the power had been disconnected. This is not the plot for an apocalypse movie, but history. So what caused this series of strange and dangerous events? And the answer to this is a coronal mass ejection, often called a solar storm when it hits us. You may also have heard of space weather. Well, a coronal mass ejection is a form of space weather. So coming up in this talk, you will discover what a coronal mass ejection is, how likely it is that one will hit us today, and it's more likely than you might think, what the effect would be if we did get hit, and how we can prepare for this. Finally, I will give you a small taste of my research and how it could help us to prevent something like this happening. So what is a coronal mass ejection? Well, this is. Simply put, a coronal mass ejection is a huge, and I really do mean huge, explosion on the sun. This video shows you just how large coronal mass ejections can be. If Earth was seen on this video, it would be so small that it would barely be a pixel in size. To understand where the name coronal mass ejection comes from, we'll break it down into simple parts. So, ejection. An ejection is a throwing out of something. You may be familiar with the term ejection seat. Here, the pilot of the plane is the thing that is being ejected. Mass. Well, all matter has mass, and this word is simply telling us that there is matter being thrown out from the sun. It's not just light. In this case, the matter are protons and plasma. And finally, coronal. The corona is simply the outer layer of the sun's atmosphere. So we put these three things together, and we see that a coronal mass ejection is matter from the corona being thrown out into space. Just to give you an idea of the energy involved, here's a few numbers. So the matter from the coronal mass ejection is being thrown into space at about 450 kilometers a second, which is 27,000 kilometers a minute, and 1,620,000 kilometers an hour. To give you some perspective, a commercial plane flies at about 900 kilometers an hour, which is 15 kilometers a minute, and 0.25 kilometers a second. This means that in 2 seconds, the matter from the sun will have traveled the same distance that a commercial jet does in about an hour. So I presume at this point you have a few questions. Could this happen today? What would happen if it did happen today? And can we stop this from happening? And the answer to could this happen today, I'm afraid, is yes. In fact, it's quite likely. Just how likely? Well, the chance of a large coronal mass ejection, that's one big enough that would cause damage to our way of life, hitting us in the next 10 years, is about 12%, or a 1 in 8 chance. In fact, the video you saw earlier, which I'll just set playing again, shows a coronal mass ejection that happened in 2012. If this had happened just 1 week earlier, it would have hit us. We would probably still be recovering from that today. So for the next part to make sense, we need to backtrack slightly. I've already explained that a coronal mass ejection is matter from the sun. The first matter to reach us are high-energy particles, like protons. The second matter to reach us, which travels a bit slower, is a magnetized plasma. Now, a plasma is simply a gas in which the electrons are not bound to the protons. There's no atoms. The electrons are free to move around. And as you might know, this will be important later, magnetic fields can create currents in wires. So, it's important to realize that it's not quite as bad as it sounds, because small coronal mass ejections do hit us all of the time. In fact, just last weekend, a small coronal mass ejection hit us. All it caused was some pretty aurora. However, if a large coronal mass ejection hit us, satellites could be pushed off their normal trajectory and their electronics could be damaged. Autopilot systems could be damaged. Your mobile phone, your laptop, any portable electronics. The main problems, however, would come from blackouts caused by the loss of the national grid. People like me are working hard to prevent this. Let's look at satellites and portable electronics first. One way in which a satellite or autopilot system, or mobile phone, or anything with a microchip in it really, can be damaged if it's hit by a high energy particle, like a high energy proton. What happens, as you can see in this video, is a single particle comes in and hits one part of the microchip. It damages it, it could change data, or it could short circuit. And that also creates secondary particles. This demonstration here is actually a demonstration of nuclear fission, so it's a bit more dramatic, but it gives you a nice visual representation of what I'm talking about. Luckily, this type of event would be fairly rare. However, something you might not want to think about when you're flying on your next airplane trip somewhere, this actually happens quite, well, maybe not often, but more often than you'd like. It can happen at any point in time. It's just more likely to happen when a coronal mass ejection hits us. What you see here is a transistor that was damaged in 1989 by a small solar storm. Now, as I've already said, magnetic fields create currents in wires, and that heats them up and cause fires. That's what happened to this transformer. There were huge currents induced in it, and it broke. The blackouts in Quebec in 1989 only lasted for half a day, but remember that this was only a small storm. If a large storm hit us, the blackouts could last for much longer. Now just think about that for a second. Maybe first you'll be worried about hospitals. Maybe you do some sort of business or something, and you're worried about the national grid crashing. Even thinking about this event today, how did you get here? Did you use a tube? Did you put petrol in your car? Did you use an electronic map? None of this would have been possible. I wouldn't have been able to research my presentation, and the posters wouldn't have been able to print it, and you won't be able to make dinner when you get home. Even if you have a gas cooker, you still need electricity to get the gas to your house. Also remember, those transformers I showed you, we'd need to fix those. We'd need to fix those without the full use of our national grid. Now perhaps you begin to understand the full scale of the disruption. Without power, it would feel like we had been thrown back in time, albeit for a temporary visit. We need a way to prevent this. Currently, we do quite well at protecting our microchips from being hit by high energy particles, which is great, but the most important thing for us will be a warning. With a warning, we could disconnect transformers from the national grid. They wouldn't be broken then. With a warning, we could get backup generators to places that need power the most, like hospitals. And with a warning, the recovery period might be weeks or months rather than years. And this is where I come in. What you see here is a solar prominence. Solar prominences can erupt, and this can cause or be associated with coronal mass ejections, which I've just told you about. So we currently do not understand why prominences evolve and how they erupt. At the moment, our warning system for coronal mass ejections associated with erupting prominences is basically limited to waiting for one to happen and seeing how long it'll take the plasma to reach us, which isn't really that good. So what I am doing, with the Glasgow University Astronomy group, I am studying a particular prominence, which is this thing you can see moving around on the bottom. By studying the changes in this prominence and finding out why they happen, I could help us to understand how a prominence evolves and why it erupts, which it does, as you can see there. This video was taken using the Solar Dynamics Observatory, specifically an instrument called AIA, which stands for Atmospheric Imaging Assembly. You can make videos like this yourself really easy by going to that website up there. And if you want me to show you how to do this, just come and chat to me after the show, and I'll tell you. It's quite cool, actually. This is another view of the prominence. It's using a different satellite called IRIS. This gives us sort of a 3D array of information, which sounds scary, but what it means is you simply have an image, like the thing on the left, which shows the prominence, and at every single pixel you can get spectral data out. I have 137 of these images, and these span a few hours of the prominence changing. What you see on the right are two spectral lines. These lines can tell us a lot about the properties of the prominence, such as the temperature, pressure, and density. We cannot directly measure these values that I've just told you about, but what we can do is create computational models. Each model, we decide what the input temperature, pressure, and density is going to be. What you see on the right is a synthetic spectra that has recently been created by some people in the Glasgow Astronomy group. By comparing the synthetic spectra with the spectra that is observed, the one on the left, we can figure out what looks the same. It's a bit more complicated than that, but we look for the one that looks most like it, and then we can figure out the temperature, density, and pressure with things associated with that. Now that might not seem like much, but if we look for changes in these parameters before an eruption, it would help us to understand why the eruptions happen. Instead of waiting for an eruption to happen, what we could do, we could look for these parameters. We could look for changes in these parameters, look for what we know will cause an eruption. And this could increase our warning time by hours or even days. Now, I hope you agree with me when I say space weather does affect us, and more people should be interested in solar eruptions. So thank you for listening, and try not to worry too much, because we're working on it.
See, it's petrifying. Okay, cool. Any questions for Holly? Yeah, on you go, Mark.
When you talk about the possible causes that lead from a prominence becoming an ejection, what do you have like a current working theory as the kind of factors that are involved in that kind of thing? Like, is it the size, the energy?
There's a few theories. Like I said, we don't really know much about how they evolve, which is one of the problems. There is one theory why we think it happens, which is called magnetic reconnection or combination. I always get those two mixed up. But basically, magnetic fields in the sun, they come off the surface and they form loops quite often. What happens is if these loops, they break apart the magnetic fields and they recombine, that creates a huge amount of energy which can throw material outwards. That's our best theory at the moment, but we're not sure.
Okay. Anything else?
It's not really a question. I just wanted to say that was a really, really good presentation, and you're really good at like making it so that even I understand.
Thank you.
So really nice.
Oh, that's nice. I was terrified.
So how far in advance do you think we might get a warning, and what would that let us do?
Okay, well, currently, like I said, we generally just wait for it to happen, and the matter usually reaches us in about 2 days, but if there's two in quick succession, that sort of clears the way for the second one, and that can reach us in as little as 12 or 13 hours. So that's our current warning, and hopefully, what my video is showing, the bit I am studying, that happens about 2 days before the eruption. So if I can figure out something that causes that eruption or leads to a change in the prominence that will cause that eruption, the warning time would be increased by 2 full days.
And so then on the surface we turn the electronics off, is that right?
Basically, it doesn't matter if they're on or off, because like I said, the telegraph messages continue to send themselves. That was because, currents and voltage, they're very related, and basically, if a current is induced in your wire, it creates its own power, in a way. So what we'd do, we'd actually physically disconnect the transformers so that they weren't linked to the miles and miles of wire, because the longer the wire, the bigger the current that is induced in it. So it's not just a case of turning it off, but we'd actually have to physically remove the transformer.
Okay, thanks.
So I was wondering about planes and human loss. How can that be prevented? Is there something that's being done to help prevent such an effect on a plane?
Yes. I don't really understand it because I'm not a computer person. I don't really know how microchips work. But they're doing something to it, which basically means that maybe if one transistor, I think they're called, which is like a little switch, is hit, that's not crucial. They've got like lots of different ones which will help it do the same thing, I believe. And I think there's something called radiation hardening, but I don't really know what it does. And that basically protects our electronics. Oh.
I'm sorry, do you know if this is being addressed on a policy level at all? Because I'm just wondering, like, if you gave me like a 2-day heads up, like, oh yeah, you're not gonna have electricity for we don't know when, in 2 days, things might get a little chaotic.
Yeah, I don't really know what the politics is behind it. I know that America is saying they should do something about it because their national grid is much worse than ours and much more susceptible to completely breaking, which is why they always have blackouts. So the American government knows that they want to do something, but I don't know if they actually are doing anything.
Okay, cool.
Okay. Yep.
So you mentioned that, like the recent one you gave us, like the pretty lights in the sky.
Yeah.
Would that happen then on a much larger scale?
Oh yes, remember at the beginning, the whole in the middle of the night thing? That happened as far south as Cuba. Like normally you can barely see it in Shetland, but in the north of America, people were reading their newspaper in the middle of the night by the light of the aurora?
Yeah, you?
How many transformers are there on sort of national grid, and how easy is it to disconnect all of them?
No idea. I'm going to guess quite a few, maybe thousands.
Like, with 2 days' notice, could you realistically?
I presume so. I think there's implementation in place where maybe there's like physical switches, like where they take out pieces of the wire. You wouldn't actually have to move the transformer.
Yeah.
I genuinely don't know the answer to that, but I can look it up.
Okay. Again, let's say thanks very much to Holly and to everybody else. So that's us done for today. We're